Let's take a look at a free body diagram that shows all of the forces on a car's tire as it drives. The diagram shows a clockwise rotation, indicating that our car is moving forward. The frictional force is responsible for the forward movement of the car, so it points in the same direction as the car. There are also forces with Y components in the diagram, the force of gravity and the normal force. These two forces oppose each other and are equal in magnitude. We can use these forces to calculate the stopping distance of the car if the brakes are applied steadily so that no skidding occurs. Notice that as the brakes are applied, the direction of the static frictional force is reversed. Using energy and work equations, we can easily derive an equation for the stopping distance. We know that the static frictional work is equal to the static frictional force times the distance the car travels, and that the kinetic energy of the car is 1/2 mv squared. We can say that the kinetic energy of the car is equal to the static frictional work. This is because enough work must be done to reduce the car's kinetic energy to 0. Let's take a look at the stopping distance of a car going fairly fast. Compare this to the stopping distance of a car going relatively slow. The stopping distance is reduced when the speed of the car is reduced. We can use the equation we derived for stopping distance to see exactly how far the car went before it came to a stop. Say that the car was traveling at 15 meters per second, and we assume that the coefficient of friction between the road and the tires is 0.8. Plugging these values into the equation, we're able to find that the stopping distance is 14.3 meters. Let's run through the equation again, but this time we will see what the stopping distance is when our car is traveling at half the original speed. We find that the distance is 1/4 of the original stopping distance. So when the velocity is halved, the distance is only 1/4 of what it originally was. So we know how to solve for the stopping distance of a car when it applies its brakes so no skidding occurs on a flat road. But what happens when the car travels around a banked turn? Here we can use the static frictional force to calculate if the car will safely make it around a turn. Let's take a look at the free body diagram. Since the road is inclined, the normal force is at an angle. The force of gravity, however, is still straight down. Since the road is a banked turn, the car experiences a centripetal force as well as a frictional force. The centripetal force is center-seeking and points towards the center of the turn. On an incline like this, the car would slip into the center of the track if static friction was not present. Therefore, the frictional force points outward at the angle of the inclined road. Knowing all of these forces on the car, we can solve for the slowest speed that the car can travel without falling into the center of the track. But first, we have to separate these forces into their x and y components. The force of gravity only has a y component. The normal force, however, can be split into x and y components, knowing the angle of inclination. Looking at the free body diagram, we can see that the y component of the normal force is n cosine theta. The y component of the frictional force is f sine theta. The x components include n sine theta and fs cosine theta. Let's set up our equations involving y components. Since the car does not move in the y direction, the sum of the forces must be 0. The downward direction of gravity opposes the upward direction of the normal and frictional force. Similarly, there is no movement in the x direction, so we can set our x components equal to the centripetal force, mv squared over r. We solve for the normal force with our y equation. Then, we can substitute this in for the normal force in the x equation. We can now solve for v. Notice that the mass of the car cancels out of the equation. The v that we have solved for is the slowest speed necessary to safely make it around the inclined turn. If the car travels faster than the speed, it will not fall into the center of the track. But what happens if the car goes too fast? There are limitations on how fast the car can go to safely make the turn as well. Let's take a look at the free body diagram once again. This time we will solve for the fastest speed that the car can go. Notice that in this diagram, the direction of the frictional force has flipped to oppose the outward motion of the car. Its sign will change in our equations. We derive a similar equation, but notice the change in signs due to the change in the direction of our frictional force. Let's solve for the speed given values. The magnitude of gravity is 9.81 meters per second squared. The coefficient of static friction is 0.8. The angle of inclination is 45 degrees. And the radius of the turn is equal to 15 meters. Plug these values into the equation for v and solve. "36.4 meters per second is the fastest speed that the car can safely go. Now let's solve for the slowest speed. Plug the values into the equation for the slowest speed. We find that the car has to go faster than 4 meters per second so that it does not fall off the road. So we know that at speeds of less than 4 meters per second, the car falls into the center of the turn. At speeds greater than 36.4 meters per second, the car flies off the road. And at speeds in between these values, the car makes it safely around the turn without exploding.